Thank you guys for attending this presentation. I'm Mitja, CEO of Across Security. Been here before for a few years ago for binary planting talk, and we are breaking into banks and presenting all such stuff. And today I will show you how we can break the monopoly of big vendors who seem to be the only ones who can patch their applications. Now, we're going to do that too. Now, the current situation you're probably aware of. We've been, and probably many of you have been finding vulnerabilities in software for a long time and reporting that to vendors one way or the other. And what we see, and what you probably see as well, is that the same types of bugs are being found over and over again, like buffer overflows, double freeze, and use after free, and so on. So the same types of bugs, and they are being fixed, and they are being found again. And the clever people find exploit mitigations that make exploiting these vulnerabilities harder, and then clever people on the other side try to find bypasses for those exploit mitigations, and it's just an endless game. It doesn't seem to solve anything because basically security-wise, we're in the same state where we were 15 years ago. On top of that, few vendors, just the big ones, are proactively looking for vulnerabilities because that's a costly process, and it costs them money to find vulnerabilities, it costs them money to fix them and to deploy the fixes, and they would rather be doing something else. And if you're reading, and of course you are, about breaches, you see that the vulnerabilities that are being exploited to break into big banks are not some fancy zero days. They are very, very old vulnerabilities that have been patched a long time ago, just patches have not been applied. We'll see why. Now, if you're a security researcher and you find a vulnerability, try to do something with that, you learn very quickly that you are perceived to be part of the problem instead of part of the solution. And to sum it all up, nobody's really happy, except for those who are trying to break in. Now, two short stories. The first one, a short story about an attacker. This is how an attacker sees his objective. A lot of vulnerabilities to pick from because the updates are not being applied. And why are updates not being applied? Well, because if you're a home user, of course you just click OK and try and wait till your computer is restarted. But if you're in an enterprise, you don't simply do that. You have to test those updates up to the point where you're confident with applying them to across the network so that they don't break your production, that they don't break your business model. And this guy knows, and we know, that current anti-malware solutions are not effective. I mean, if you want to bypass those, you just need to take some time and do some testing, and you can always bypass anti-malware. Now, this is what we've been doing for 15 years, and we still do this, and we're kind of frustrated that this still works, and it's just not getting any harder. If you are hired to penetrate a target, you find a vulnerability in a software that they're using, which is usually Windows, because in large corporations, that's usually Windows that they're using. And you find a vulnerability that's not too old, so let's say up to 2 months old, which means that you have a lot of vulnerabilities to pick from. And you prepare an exploit for that vulnerability, and finally you mutate that exploit and keep sending it to VirusTotal until VirusTotal does not detect it anymore. So you know that basically whatever protection they're using, whatever detection of exploits they're using, is not going to detect you. And then you fish until you're in. So you keep sending users in that organization links to a malicious website which is going to exploit the vulnerability. It's really simple, come to think of it, and the fact that this has not changed in 15 years, in spite of all the new technology that's been invented and is being sold for billions worldwide, this is kind of frustrating. Now, the second story is a story of a security researcher. How many security researchers here? Okay, and some of them not wanting to admit it publicly. If you find a nice zero-day in some applications, a popular application, what do? It's a dilemma. There are actually no good options for you. And these are the options. Well, apart from applying for a bug bounty. These are really popular, but they don't really pay very much. These are the options. Number one, you can responsibly disclose to the vendor. So what happens there is basically somewhere in the spectrum from complete silence, you don't get no reply, to thank you very much, we'll attend to this when the time is right, to basically on the other extreme, you have a meeting with their lawyers, which is not very nice. So you can get any of these. Second, you can publish. You can just go to a conference like this and say, I will drop a 0 day here, so for your amusement, right? I will not do this today. But yeah, people do that for exposure, and, well, you might want to do that, you may like it or not. You can get someone angry doing this, up to the point of them wanting to talk to you in a very small room. And number three, you can sell the vulnerability. Good 0 days go for a lot of money these days, but there's always a problem of trusting whoever you're selling to, and the bigger problem if you don't have ethical reservations, a bigger problem that you may be found guilty of helping someone commit a crime. That's not a nice option. And number four is just to forget about it, put it in a drawer or a shelf if you want, and then what's the point of your exercise? So no good options for the researcher today. And why is all that? This is the reason. Patching security vulnerabilities is a hard problem, and it's never been really solved. Why is it a hard problem? Well, these three players, software vendors, users, and security researchers, just don't seem to have a way of really living together, of working together in a very, very constructive way. Software vendors have and want to keep the monopoly for patching their own software. And they are the only ones who can decide whether to patch, when to patch, how to patch, and when and how to deploy, and for how much money to deploy that patch to end users. So a lot of things going on, and they would rather be doing something else, because this is just a cost for them. They would rather be earning money somewhere else. Now, users, how many of you like Patch Tuesday? Well, no hands, right? Nobody likes Patch Tuesdays, right? Nobody likes reboots and downtime. Even if you're not some huge production that you would lose millions of dollars for that reboot, you don't like that. Now, for the large networks, it's really a lose-lose situation. If you do update immediately, then you risk breaking your production. If you don't update immediately, you risk being broken into. Because, as you probably know, just a few days after official updates are out, some interesting exploits come up in exploit kits. So if you have a couple of $1,000s extra, you can just wait for a couple of days after the Patch Tuesday, and you will get fresh, working, quality assurance, tested exploits for some of these vulnerabilities. So it's really nice. And the security researchers aren't really happy as well. Because, let me tell you, every security vendor, every software vendor in this world would rather see the world without security researchers, because we are just causing problems to them. If we did not exist, there would not be any vulnerabilities in the world. So yay, right? Now we are being considered a part of the problem. And this is why those stones are very hard to stand up. And out of that frustration came our idea. We want to reinvent software patching. Because the software patching as it is today, it doesn't work. It works in that slow glacier speed way, but it doesn't work for critical vulnerabilities that need to be addressed right away. Now, our idea is that everyone should be able to just use a couple of minutes to install a small piece of software, we call it Zero Patch Agent, that will apply tiny security patches. I'm talking tiny, I'm talking a couple of machine instructions, not gigabytes of code, which you usually get every Tuesday. And that agent will apply tiny security patches in the same way. And in the same way, I mean not on the disk, but just in memory. Just when the process is running, patching in memory, which means also unpatching in memory, and it can be done instantly. In the same way for all applications. Wouldn't that be nice? And then you could apply and remove those patches instantly without rebooting the computer, without restarting applications. and in an enterprise, without disturbing the users, and without even disturbing the admins. So if someone notices that something's wrong with that micro patch, it can be instantly removed. Now compare that, anyone being an admin in a large enterprise? Okay, you guys know. Do you dare just applying patches? You do? Yeah? How do you like when someone says, I want this patch removed, and this guy is on a laptop 500 miles away? That's really nice. It's a nice task for you. So yeah, that's our idea. And I'm going to show you how it works. Okay, I have a computer here with very low resolution, as you can see. And it has a zero-patch agent installed. This is the console. And it's currently disabled, which means it's not applying any patches anywhere. Now, I also have a couple of vulnerable applications installed and a couple of exploits. So let me just start with something that you will immediately laugh at. I'm opening a fake New York Times page that's using an old Java vulnerability to run the calculator. As we all know, the calculator is the most malicious application on all Windows computers. You should immediately remove it. So this was an example of a malicious web page exploiting a vulnerability on your computer immediately as you drove by, basically. Now, this is without the zero patch. Now, I'll show you another example, a Foxit reader. I'll just open a Foxit reader, an old version, of course, a vulnerable version, and drop an exploit in it. Now, we just crashed here. We did not pop up the calc. But let me tell you, this is a vulnerability, a buffer overflow that we're exploiting here. Now, what I want to show you, if I enable zero-patch agent, things are going to be a little bit different. I'll just go to that malicious New York Times page again. Well, hopefully. Okay. Now, in contrast to that calculator, this time, as soon as Java was launched in the background, it was immediately patched by our agent, so that vulnerability was no longer there. And apart from that, the patch did not just plug the hole, it also detected that someone tried to exploit the vulnerability and was able to alert the user that exploit attempt was blocked. Now, this is shown 5 times because this vanilla exploit that we have tries to exploit the vulnerability 5 times. Those of you familiar with exploits know that some exploits are not very, how do you say? Sometimes they don't work, and you have to try a couple of times. Now, same thing with the Foxit reader, and I will show you something else so you can understand what I'm talking about. I will change the settings of zero-patch agent to inform me about all patching events, which means that it will tell me whenever a patch is applied to any running application. So as soon as I launch Foxit, you will see in the top right corner a pop-up that a patch was applied for Foxit reader, just in memory. We have not changed a single byte on the disk. Now, when I drop the exploit here, the exploit attempt was blocked. And importantly, again, it does it twice. And importantly, Foxit keeps running, right? And let's try something else. Now we know that Foxit is patched currently. Let's unpatch it. We go to Applications, find Foxit, unpatch Foxit reader. As soon as I do that, Foxit is running in the background, and you see patch has been removed while it's running. So this is what we're talking about. Patching being applied and unapplied in memory, nothing stored on the disk. This is what allows us to do it instantly. And this is what allows admins to do it remotely, also instantly, without even on laptops 500 miles away. Okay, let's go back to the presentation. Now, how does it work? Anyone familiar with function hooking? Okay, very good, very good. So the concept is pretty much the same here. The difference is that we do not only patch at the beginning of the functions, but anywhere in the code. Now, suppose this is code. Don't be afraid. This is machine code, no problem. It's code as any other code. And let's say that we've done our analysis of the vulnerability, and we've come to the conclusion that we want to inject some patch code that will do some correction after this call. Now, so we need to inject our code after this call. And we see that the following three instructions are suitable for relocation. What does that mean? That means that these instructions can execute just as well here as anywhere in the memory because they are not using any relative offsets. And what's important also, that no execution branches actually come back into these instructions, because if you move such instructions, you will break something. Now, if we know that this is a suitable location for our patch, we're just going to take these three instructions out, put them somewhere else in the memory, put our patch code before these original instructions, just make a simple jump from that location where the original code used to be, jump to the patch code, and then back where we used to be, right? So effectively, we just added some code to the original code. And that is the idea of patching, basically. Most bugs can be patched by adding some code. Like if some programmer that caused a buffer overflow vulnerability forgot to check for the length of the input buffer, now we do this checking for him. So what do we need to define a patch, basically? We need to know which module to apply it to. By module, I mean an exe file or a DLL file or an SO file on Linux. And we need to know the hash of that module so that we don't accidentally patch something else, right? So we know that the module has been loaded, so our agent knows that the module has been loaded, and he also needs to know where exactly inside that module the patch should be injected. And also, obviously, what code should be injected. It's really as simple as that. Now, this is a sample patch code, source code, right? We need to define the module path. In this case, we have app.exe, which is vulnerable. And it's vulnerable. We want to patch it at this location, in this offset. And this is the code that we want to inject. So we're just putting 0 to EAX register because we noticed that it was not initialized correctly. So someone found a way to exploit this. And this is a very simple patch code. And they all look like this. They'll only have maybe more instructions than just one. Now the question, what can be patched this way? Obviously not every vulnerability can be patched, but what can be patched? Fortunately, it turns out that this way of patching is suitable for almost every remotely exploitable vulnerability. But let's go first through those vulnerabilities. Those are the typical vulnerability types which we're all familiar with. Use after free, double free, numeric overflows, underflows, buffer overflows, format strings. Uninitialized variables, for instance, that previous example. This is an example of initializing a variable that the programmer forgot to initialize, for instance. Binary planting bugs just don't seem to be going away, or DLL injection bugs don't seem to be going away. We can do a lot of things with these patches. You can basically do anything with these patches, but if you want to keep them small, you are kind of constrained to what you can do. Now, very unsuitable for this kind of patching are scripted code, for instance, on the servers, PHP, Ruby. You can't patch that easily this way. This would have to be done in another way. Design flaws, if there's a vulnerability that exploits some really incorrect design of an application, you probably cannot patch that with just a few bytes of code. You cannot patch Windows kernel because the Windows are actively defending against that with PatchGuard. And you also have apps. We have come across just one so far, which is Skype, that hates patching itself, hates to be patched. So it detects that it's been modified and it crashes. Well, they have reasons for that, but just one out of hundreds of apps that we've seen. Now, we refer to zero patch as being microscopic cure for big security holes. So remember that. We are patching just adding a few machine instructions to the original code. And a lot of benefits in that, as you will see. Now, let's create a patch for an integer overflow. Let's see how that works. We have an old Firefox installed here with an old vulnerability in the reduce-write function. Reduce-write function works on an array, and the problem is that if an array is really long, which means that it's more than 8000000, I don't know if I put enough zero in there, elements in that array, or if its length is larger than that, then we get an integer overflow. And the integer overflow basically comes from the fact that we have an unsigned integer used for the length of that array, and a signed integer start, which is then later assigned that length minus 1. So what happens in the following case, we'll go back to the source code. This is a simple proof of concept that crashes Firefox. We create an array, we give it a length of 8010, just it has to be more than 8 and 7 zeros, just to make sure that as the signed and unsigned integer representation of that number is not going to be the same. And then we call reduce write on that. Let's see what happens. So, going to turn this back on. And we're not currently having any patches for Firefox here. So, I'm launching Firefox. I'll make it a little bit smaller for you to see. And I'll drop this HTML, which is that simple proof of concept that I showed you. And it's a crash. Right. So what happened here in the code is basically that this length of the array, which was determined by this call, was a very huge number, but that's okay for an unsigned integer. However, when it was converted to a signed integer, it became a huge negative number. And then all hell breaks loose. So, our question was, how do we patch this? Well, a typical way to patch numeric overflows is to make sure that the number that should not be too large is reduced to a legitimate size. So what do we do here? We find in the machine code where this call gets executed. So we found the call, which is here, right? And after that call, with a little bit of debugging, you see that the length of the array, which is determined by this call, is stored in memory at the location pointed to by the EDI register. Sounds complex, but it's really not. Now, right after this call, very conveniently, we have 5 bytes, 2 instructions which can be easily relocated. Now, what do we want to do? I just put apart the code here to make room for additional code. And the additional code is just this. So that length of the array, which was just established by the call to that function, is now logically ended with 7FFFFF, which means its highest bit is being reset. The result of this is that this number is always going to be small enough to have the same representation as a signed and an unsigned integer. Now let's see how that works in real life. I have this patch source code conveniently prepared for you, and it's here. So this is actually the module that has the vulnerability, and we can skip these uninteresting parts. And this is the offset in the module where we want to add our patching code. And this single line here is the patch code. So this is the code that we want to add to Firefox. Now let's actually add that code to Firefox. So I have it in this file. So I will launch zero patch deployer. On that file. Okay. it's just going to compile that source code into an actual patch. The actual patch currently is stored in registry because it's so small that it can actually be stored in registry even if you have tens of thousands of patches. And now, if we look in the registry, these are the patches. These used to be the patches just before my operation. And if I refresh here, we'll see a new one here. New patch for this hash of the module. This is the ID of the patch. And this is the code. We're just injecting 6 bytes of code at this location. Now let's see how that works. So we have Zero Patch Agent enabled. And we're going to relaunch Firefox. And as you can see immediately, it says that the patch was applied to Firefox. Now let's drop that exploit in there. What did I do? Oh yeah, it did not crash. But it also did not pop up the exploit alert, right? And why? Because we did not put that call in the code. It's not automatic. You have to put it in because you may want to have minimal patches without those calls. Okay, now let's do that. Let's change that. So, okay. Let's make some more room for some more code and put this in. Instead of just simply logically ending the array length, we'll first compare that length to see whether it's too long. And if it's not too long, we are done. But if it is too long, we're going to reset its top bit, and we're also going to call exploit blocked. Now, let's do this. I have this prepared in this second file. So this is the only change is that I put this code in. Now let's compile this. It's just going to overwrite the patch that is already in there. And now let's launch Firefox. A patch is again applied, as you can see. I'll drop the exploit to Firefox. And yeah, the vulnerability is no longer there. And besides, we were able to detect that someone tried to exploit this vulnerability. It could be useful information. Right, so we patched a numeric overflow here. Now let's patch a buffer overflow. It's going to be more difficult because we don't have the source code here. Firefox is nicer to patch because you have the source code, while oftentimes you do not have the source code for patching third-party applications, but we'll still try to do it. Let's say I took an all-player vulnerability. It's a media player. It's a vulnerability in parsing the playlist file, M3U file. In that file, you have individual lines of URLs to media resources. So what allplayer does is it goes through each individual line and starts to process it. But first thing it does, it copies that line to a buffer on a stack which has a fixed size of 260 bytes. And obviously, this is a very simple proof of concept because there are more than 260 A's here. Let's see what happens. Let's go back to allplayer. I have a nicer exploit here for you, so wait for it. Yeah, we got a calc here. So it's a very simple vulnerability. If someone has allplayer installed and you send him this file and he opens that, there's calculator running on his machine, and we know what that means. Okay. Now, I won't bore you with all of this code. What you need to understand here is the second instruction from the top is a call to string lem, right? And this is the call that returns the length of an individual line in that file. And this line is exactly what we're exploiting. We're creating a much too long a line. And at the end, we're calling string copy, which means there is a fixed size buffer on the stack of 260 bytes space. And we're just simply string copying that to the line to that buffer. Now, our problem, obviously, the vulnerability here, that the line can be too long. Now, what do we want to do? We want to shorten the source buffer before that string copy call. So we make sure that even if the line is too long, we're going to cut it short by putting a 0 at the very end of what would be allowed. Now we see that these bytes are suitable for overriding. Well, we know that you would have to do some thinking, but it turns out that these are nice for overriding. Let's just move this code to the top, put it apart, and this is the code that we want to inject. If you saw in the previous slide, ESI register happens to have the length of the line stored in it, +1. So we can use that information to see whether the line in the file is too long. So we just compared ESI to 104H, which is 260. Which means we are checking whether the original line is too long for the destination buffer. And if it's not too long, we say we're done. So if it's exactly 260 or less, then it's okay. But if it's not, we're just going to put a 0 in the source buffer. So when the string copy is called, it's not going to overwrite. It's really that simple. And we're also calling exploit blocked, so we know that someone tried to exploit this. Right. And we determine that the module is allplayer.exe, and we know where exactly in the code we want to put the patch. Now let's actually do that. This, again, is the source code of the patch. This is the module, allplayer.exe. This is the offset. The hash is being automatically calculated by our tool. And this is the code we want to inject. It's really very simple, and most of the patches look like this. Very short, small amount of code, because usually you just have to correct small oversights from the original programmer. Right. Let's patch that. Okay. And the patch is done. So it's in the database, and whenever allplayer is launched, it's going to be patched. So let's just launch allplayer here. And we see, okay, a patch is now applied. Now I'm going to open it with an exploit. And instead of the calculator, you will see exploit attempt blocked. Now, we have just patched a buffer overflow with a patch that can be instantly applied to an application while it's running and can be removed from the application while it's running. No reboots, no restarts. Now, in experimenting with these patches and this technique, we have created a couple of guidelines, a couple of rules that we need to adhere to in order to make this all worthy of end users. And these are the 5 patching guidelines. First one, you have to obviously find a good place for patching. Not all, you obviously have a selection of places. Once you understand the vulnerability, you can patch here or here or here or here. You have to decide which of these locations is the best. Because you want to cover all of the possible exploit paths, but you don't want to cover anything else. You don't want your code to be executed unless absolutely necessary. And of course, you have to find a place where you can actually, where there is some relocatable code in the vicinity that you can use for injecting your code, your patch code. And obviously, the original code that is going to be relocated has to be relocatable. It's a big problem if it contains any relative jumps, because you have to recalculate everything. And if it's moved too far, then you cannot jump back and so on. It's not really very important for right now. The second rule is you don't want to break anything. I mean, who is going to want a patch if it patches a vulnerability but creates another problem elsewhere. It may not create a vulnerability, but if your application is going to start crashing, then you don't want a patch like that. You're okay with the solution that you have right now. So you should make no assumptions about how the code that you're patching is working and where all the execution paths could lead to your code. You actually have to do the analysis and do the debugging and do the statistical analysis to see all the inbound and outbound paths. And obviously you have to preserve the original functionality. Sometimes you find a bug that you can only patch by actually cutting off some functionality. We've seen, for instance, shell shock, bash, the bash vulnerability. Well, almost no one in the world was actually using the functionality that was being exploited in shell shock. So the initial patch from the original bash developers was to actually cut off that functionality, which is okay. You can do a patch like this if it works for you. But usually you want to try to avoid making any functional changes. And you also have to make sure that there are no side effects. So if you're changing any registers or flags with your patching operations, you have to make sure that that does not have any negative effects on the code, on the original code that continues executing afterwards. Rule number 3, the patch should be as small as possible. Why? Let's say patch Tuesday. You get 600 megabytes of code, right? Downloaded to your computer, which replaces, a big chunk of whatever's running on your computer. It's impossible to review. It's impossible to make sure there are no errors in there. And if we make a patch very small, then it's possible actually to review that. I can review your patch. You send me your patch with 4 instructions. I will be able to review that. Anyone will be able to review that if they know the machine code. So fewer lines of code, fewer errors. Easier reviewing and easier testing. So we want to contrast this to the patch Tuesday updates, right? We want to keep it really small so that even the admin can take a look at the patch and say, okay, this looks legit, includes no malware. That's really important as well. And less code is less execution overhead. We all know how much users like security products that slow down their computers. Yeah, no, this does not have to slow down your computer in any way. And less code is less possibility of introducing a race condition that previously wasn't there. Now, rule number 4, your code should execute as rarely as possible. So the location of the code, of the patching code, must be chosen very carefully to make sure that it's just executed when it's necessary and not when possible, not in a very long loop. So it doesn't get, if for instance, you have an algorithm, an implementation of an algorithm that does some heavy processing of a very large chunk of data, you may want to put your patch code outside the loop because then it's going to be executed just once. If you put it inside the loop, it's going to be executed a lot of times and it may slow down your computer. And now rule number 5, you have to test for security and functionality. So when the patch is deployed, it first has to resolve the problem, obviously, that's why it's there, and it has to, it has to keep the original functionality intact. Now, the point of this presentation is to change this guy who was not sure what to do with the vulnerability found into someone who will decide to create a zero patch for it, because that will be, arguably a very ethical thing to do. And also, it will be a possibility in some time to actually make a living out of patching someone else's code. And that is actually our goal. And we'd like to change this to this. Now, if you guys want to try playing with Zero Patch and creating your own patches, just contact us, send us your email, we'll create your beta account. It's still a closed beta, but you guys, since you're here, you're privileged and you can get the accounts that people outside this room cannot. And if you want to create patches, we'll send you the tools that you need to create patches as well. Thank you very much. Thank you for your attention. I hope I have turned at least one of you exploit developers who don't admit of being one into patch developers. Thank you. It did?
Yeah.
Oh, so my source is wrong.
What happened then was that several other people found other vulnerabilities in this functionality.
Okay.
Only then they decided to disable this functionality. So the lesson to learn is, I think, exactly the opposite of what you said. Because it was a dangerous functionality in general. And then I have a question, like, what you're doing is, you're introducing an application that is very powerful, that is able to patch other applications in runtime. So basically, your application becomes
a very attractive source of
Yes.
new vulnerabilities. So, what do you do to not become part of the problem?
Well, that's a very good question. Well, first of all, when it comes to being a security product running on a computer, we're basically in a very similar situation to other security products that are also hooking into applications. But that's true. These days, security products are being a very interesting target for security researchers, and a lot of vulnerabilities are being found there. Obviously, we need to do what everyone else does. We need to make sure that our attack surface is very small. Well, we come from a security company, and we're hoping that will reflect at least a little bit on the development of our own code. Although we're not fooling ourselves, there will be vulnerabilities in our code as well. What we're focusing on mostly is to make sure that vulnerabilities and malware cannot be introduced to your computer through the patches, because that is the most interesting attack vector. Someone trying to trick us into deploying malware to all the computers. Although the problem is again similar to let's say an antivirus product. If you break into their network and change the next update of their agent, it's going to be deployed to every computer. But very good question, and thanks for explaining that about shell shock. I actually obviously had the wrong information. Thanks.
Good morning. I would like to ask, what is the goal of Zero Patch? You would like to replace completely patching, or is just some temporal solution while the patches are deployed?
Actually, yeah, very good question again. So obviously, this cannot replace what we currently have, but this can be a very good solution for two things. Vulnerabilities for products that don't have vendors anymore, or don't have support anymore, like Windows XP, for instance, and to bridge the gap between the official update and corporations applying that official update, which can be months after that. So this is a huge gap, which always gives a lot of ammunition to attackers, right? And if you put a zero patch here on day one and keep it until you can apply the actual update, then you're kind of covered, and that's really the point.
And I will have a second question. Your product will also be seen as from other security products like malware, or how do you sort that?
Actually, we're doing a lot of testing. It's a very good question again. Since it's doing the patching, it's doing the things that look like malware, but we're not doing anything different than other security products. Every antivirus product is doing hooking, right? And it's the same kind of hooking, just not at the beginning of functions. So it's really not a big problem. We were worried about that, but it turns out that we're coexisting okay. And
so isn't there any kind of a race condition with a virus scanner? It's a behavior that you show, which is basically what malware does.
I'm sorry?
Your behavior, what your product does, is basically what malware does. You're patching.
Yeah.
So isn't there any kind of race condition with a virus scanner on the system?
There is no race condition because what the antivirus or anti-malware products are doing, they are doing a lot of hooking, but they are hooking functions at their beginnings. We're almost never doing that.
Yeah, sure, but isn't your software detected as a malware by the antivirus?
It's never been detected as malware, and we've been testing it with top 20 anti-malware solutions.
Okay.
Yes. There are compatibility issues, of course. You can always have compatibility issues. We have 2 security products running on the same system. But we're doing pretty well. Thank you. Very good question. We have a question here.
Okay, and so looks like a nice product, but I have a question about compatibility with Control Flow Guard of Microsoft. They're introducing with Windows 10.
Yeah.
And they have a list, like a bitmap of entry points where a function can jump to. Mm-hmm. So you just, if you patch that and insert some code, you will invalidate this bitmap, which will Control Flow Guard use to find out if somebody jumps to the right position.
Yeah, that is true. Control Flow Guard, we have not really tested against, so I have no good answer for this. But we are confident that if all other security products will be able to live with Control Flow Guard, then we will be able to. But actually, we can talk about it later, because I'll be happy to. That's something that's on our list of to-dos, but I'm sure it's not going to be a problem. But again, a very good question.